Let us study ESA27H, Hamilton's least action principle. We have shown that the physical path of a free particle with mass m departing from A at time ta and arriving at B at time tb satisfies the condition that is called the least action principle. The least action principle states that the action for a free particle's motion is really minimized for a free particle on the path that is physical. So if we deviate the path, keeping the two end points A and B the same, and deviate the path arbitrarily, its action evaluated between the two instances, the time integral over the whole period is greater than the value evaluated along the physical path. This is true for a free particle. That's the reason why the delta S is non-negative. And when delta S equals 0, it is flat, but delta S is non-negative. That means it has the minimum along the physical path. We have tested this idea whether it is still true in a general mechanical system. And we use a simple example that is simple harmonic oscillator. In a simple harmonic oscillator, along the physical path, if we deviate the path from the physical path, it is at leading order in delta, it was 0. That means it is either minimum or maximum. In the case of a free particle, we have proved that the minimum is true. Here, the action is the time integral of the Lagrangian, and Lagrangian is defined by the kinetic energy subtracted by potential energy. We have not used arbitrary force case. Instead, we have considered only a very simple case that is called simple harmonic oscillator. All right. However, depending on the path of variation, the delta S at order delta was 0. However, at order delta squared, from order delta squared, the sign was not determined. It depends on the variation. Sometimes it was a positive, that means a minimum. Sometimes it was negative. That shows that it is a maximum. So we actually, if it is not a free particle, we do not know whether the action is minimum or maximum when the path is physical. So the Hamilton's least action principle is true only for a free particle. However, we can be a little bit conservative to state that action has an extremum along a physical path, along the physical path. All right. We can rewrite the equation of motion F equals ma for arbitrary conservative force F. Alright, if it is conservative, then we can always define the potential energy, corresponding potential energy, that is defined to be evaluated at a certain point, and the work done by the force from this reference point to arbitrary point. So why don't we write at x prime as an integral variable? Because the potential can be defined for a conservative force, we can take the negative gradient of the potential energy to find out the force. Okay, negative gradient, negative sign is here, gradient can be expressed in a simple form in the Cartesian coordinate system. If I substitute this for the F, what we find is mass times acceleration. The negative sign becomes a positive sign if I move this one to the right-hand side. So Newton's law of motion, the second law of motion, can be expressed like that. We can multiply the variation from the physical path, keeping the endpoint the same. So we use the same method to take the scalar product with the equation of motion for an arbitrary path, and we know this is definitely zero still. So similarly to our preceding analysis for the free particle and the particle in the harmonic oscillator, we can rewrite the acceleration scalar product with the variation by applying the Leibniz rule. This is now just a repetition that have been carried out in the previous class. Instead, in previous case, we used the replacement of a force by minus kx. Now we are replacing this force by minus gradient potential. That's the difference. And you can simply follow the rule without any difficulty. So let's see, beginning with the equation of motion, the scalar product with the variation, we would like to replace this term x double dot dot delta x using Leibniz rule, subtracted by velocity, scalar product, delta velocity. Okay. Where is the equation of motion? This one. This one. This term is replaced with this. So multiplying this by mass, we find this contribution and this contribution. And then the last term, plus gradient of potential energy, scalar product, delta x. That's fine. All right, this is this, and this is this, and this is this. Now, we can make use of the endpoint constraint to simplify this relation by integrating over time interval this. And we know this total time derivative and endpoint contribution vanishes because this variation of the path is allowed only for t is not equal to endpoints. All right. Therefore, this integral is left. Now, we can again replace this velocity scalar product with the delta velocity. Again, Leibniz rule, can be used to express this one as the variation of the kinetic energy. Now, the variation of the potential can be evaluated. Variation of the potential is potential energy evaluated along the path x plus delta x subtracted by the potential energy evaluated at a point on a physical path. Now the gradient can be used to re-express this variation. All right. Finally, this one is the variation of the kinetic energy. Variation of the kinetic energy. Integral. This one? No. This one? This guy is nothing but the variation of the potential energy. So what we find by neglecting order delta squared contribution, our equation of motion, modified equation of motion, this guy is nothing but this variation of the integral, definite integral over the time interval, TATB, for the Lagrangian. That is, what's that? This is action. Variation of the action is 0 at the 2 order delta. And 2 order delta squared, nobody knows, because we have found the counterexample that action is not always minimized as long as the non-vanishing force is applied, because we have a single counterexample called harmonic oscillator. Therefore, Hamilton's least action principle is true only for a free particle, but the action is an extremum. So extremum condition is true in every case. That is 2 order delta instead of 2 order delta squared or higher. That's it for today. We are left with a single lecture. The last lecture will be given soon. Thank you. That's it for today.